Hey everybody, thanks for watching my TED Ed video. I just wanted to make a quick follow-up video so I can explain some of the things. I'd seen a lot of questions asked in the comments. Thank you guys for your questions and your comments, and I just wanted to address some of them. So the first comment I had received a number of times from a lot of you guys is that you didn't see where some of the other numbers came from when I was doing the matrix multiplication. Now, when I did that originally, I kind of showed how to do the first ones and said the other ones sort of follow the same way, but I figured you guys might benefit from me taking it a little bit slower. So let's take a look. See, I got a bunch of these ready. So the one that I had done originally was this matrix times this matrix. These are the ones that you see in the video. And remember that the way that you multiply matrices is you take two numbers, say for this first entry right here. This entry is in the first row and the first column. So in order to get this entry, you need to use the numbers here and here. So what you do is you kind of go to the beginning and you multiply. 1 times 2 is 2. 3 times 3 is 9. And then what you do to get this one is you add them together. 2, which is that product, plus 9, which is that product, equals 11, which is this product here. And that's where the first one came from. So let's actually work through the other ones as well. To get this one, we work with this row and this column. So go all the way to the beginning, all the way to the beginning. 1 times negative 4 is negative 4. 3 times 0 is 0. So negative 4 plus 0 is negative 4. And of course, since this is YouTube, please feel free to pause the video, rewind it if you need to, if I'm going too slowly, and of course you can always respond to this video if you've got further questions after that. So, let's do this one. This one we've got the second row and the first column. So we go to the beginning, go to the beginning. 2 times 2 is 4. Negative 1 times 3 is negative 3. So 4 plus negative 3 is 1. And, by the way, my hands aren't getting in the way, are they, or anything, Mike? Alright, cool, just making sure. Alright, and then last one, we need to get this one. So this one corresponds with this row and this column. See, the idea is where you are in the matrix kind of suggests where you need to go, which row of the left matrix you need to use, and which column of this matrix you need to use. So it kind of lines itself up. So, one last one. 2 times negative 4 is negative 8. Negative 1 times 0 is 0. So negative 8 plus 0 is negative 8. So, that's where those other three numbers came from, hopefully in a little bit slower of a pace, so maybe that makes a little more sense. So to get each one, we used the row and the column that were the same as that entry in order to get it. Now, something I wanted to address real quick, you're used to, when you're doing basic multiplication, you know that, for instance, 2 times 3 is 6. And you also know 3 times 2 is 6. And so that's what we usually call commutativity. We say that multiplication is commutative. But as it turns out, if you notice, here I've got the exact same one. Here's this matrix I just put here instead, and this matrix I put here. But as it turns out, multiplication isn't commutative with matrices, and this is going to be important for something I'm going to come up with later. But let's work through this one. And remember, again, you can pause if you don't see where the numbers are coming from, but I'm going to take it step by step. 2 and negative 8, add those together, we get negative 6. 6 and 4, add them together, we get 10. 3 and 0, add them together, of course, that's 3. And then 9 and 0, that's 9. So we use the exact same matrices, but we put them in a different order, so we ended up getting two completely different products. So that's something to be careful of when you're doing matrices. You can't just switch the order like you can with regular multiplication. Alright, so that's the first thing I wanted to go over. Second thing, a lot of you guys had questions about what sizes of matrices could be multiplied. You noticed that when I did the math rules cryptography example, I had a matrix that had 4 values in it, a 2 by 2, 2 rows by 2 columns, being multiplied by a 2 by 5 matrix, meaning 2 rows and 5 columns. And you're saying, well, don't they have to be the same size? If you go back to the video a little bit, I actually didn't say they had to be the same size. I said they had to be the right sizes. And then the important thing is what it means to be the right size to multiply 2 matrices. The idea is, if we look at the two, like, take a look. This is the one that was done in the lecture. And this is what we would call a 2 by 3 matrix. I mean, you've got 2 rows and 3 columns. And then we wanted to multiply this by a 2 by 2 matrix. Now, the way that matrix multiplication works is in order for a multiplication to be valid, these 2 numbers actually have to be the same number. It's not that the whole dimensions have to be the same, just that the inside 2 numbers have to be the same. And usually the way that's presented in a class is they tell you this, and then they tell you just to memorize that the 2 numbers go together, and that they have to be the same, and otherwise you can't multiply them. I wanted to show you guys a more kind of intuitive approach of what's going on. So the idea is we're trying to do this matrix multiplication, and so we want this element right here. So you go to the beginning, and go to the beginning. 2 times 8 would be 16. 3 times 4 would be 12. And then we move to this one, and suddenly there's no more room here. And so that's what we were talking about. The idea is, this matrix has 3 columns, but this one only has 2 rows. So those couldn't be multiplied. Whereas something like this could be multiplied, because if you notice, you've got 2 columns on the first matrix, and 2 rows on the second one. And so, in order to multiply these, you would just take each one of these elements and do exactly what we were doing before. So like, I'll do a couple of these, but for instance, for this one, you would do 1 times 3, okay, it's 3, and negative 4 would be negative 1, or like for instance, for over, yeah, that's right, and then for over here, you would do 3 times 0, so that's 3, and then multiplying here. It's late, I'm taping this at about midnight, but anyway, okay, so 0 plus negative 4 is negative 4. So you kind of see how this would work. And if we wanted to write out the dimensions of these just to make sure, remember we said this is rows by columns, so this is 3 rows by 2 columns. And then this one is 2 rows by 3 columns. So since these numbers match up, the multiplication is okay, and as it turns out, 3 by 3, if you look at the other 2 numbers, that's the size of the matrix you end up getting. But the nice thing is, you don't even have to remember that. All you have to do is line them up this way, and it kind of naturally falls into place is the idea. So, alright, so that's that. Okay, one other thing that I wanted to go over with you guys. People were talking about applications. Some people asked, so why do matrices multiply this way? Well, matrices kind of were invented to multiply this way. Like, when they were coming up with matrices, the various people who worked with them, they designed the multiplication so that it would do things that we as humans needed to do in our tasks with multiplying things. A really common example of what this is really used for, and usually the first thing you get into after you've done matrices, is systems of equations. So take a look at this system of equations right here. This is something you'd usually see in an Algebra 1 class, where you've got just a basic system of equations with x and y, and then you have 2 different equations. So we say it's a system of equations with 2 equations and 2 unknowns. Now, as it is, you've probably learned a number of ways to solve this. You've learned how to use substitution to do this, and you've learned how to use elimination to do this. But using matrices gives you a really convenient way to do this. And like I said, it's going to turn into one problem. So take a look at this. I'm going to show you how this is set up, and then we'll kind of run through it. Let's say I had a matrix that I just plucked off these numbers. So 4, -2, -7, and +2. By the way, can you see how much time I'm running? Does it say anywhere?
10:30.
10:30? Okay, yeah, we're doing good. Alright, don't want to take up too much time, but I figured this might help. Okay, so this is this one. And now let's say that this matrix right here, I'm going to leave it wide and you'll see why. This is still a 2x1 matrix. I'm just leaving some space. And I put x and y. And x and y are my variables here. Right? So, the answer, of course, the product of those two matrices, when we multiply them, would go here. So take a look at what ends up happening. 4x, so we're looking for this area here. In fact, actually, let me make sure you can see that. So for this entry right here, 4 times x, -2 times y. If we add those together, we actually can just write it down just like that. 4x minus 2y. And then this one right here, -7 times x, +2 times y. If we add those together, we get, just like I said, -7x plus 2y. And if you notice, these things right here are the left side of the equation that we just said. So what we can basically do is we can say that this should be equal to it's -6, -12. Now, what that lets me do is I've now turned this into what's called a matrix equation, where I've got this matrix times this matrix equals colors -6, -12. Alright, so let's say we called, let me make that a dot so it doesn't look like it's another x. So let's say this matrix we could call A. So that's A. And this matrix we could call X, since that's got our variables. And we'll call it capital X, since our variables are little x and little y. And then we'll say that equals B. We'll call this matrix B. So what we've managed to do is we've taken this system of equations right here that had a bunch of different things. This was 2 different equations, and we've reduced it down to 1 equation. And this could extend so many different ways. In real life, you might have, say, an equation that has 12 different variables and 12 different equations, but if you put them in a matrix, it still goes down to 1 equation, like that. So, the question is how we would solve this equation, and this is going into the last thing I wanted to go into. I'm going to actually move the B over a little bit, and you'll see why in just a second. Now, if you were doing this in just a regular algebra class, the way you would solve for x is you would divide both sides by a, if those were just variables. Like if it was like 3x equals 6, you would divide both sides by 3. And so we would divide by a, and we would get x equals b over a. Right? But the problem is, with matrices, we actually can't divide for a couple of different reasons. First of all, realize that when I'm doing something like 6 divided by 3, that's just like saying 6 times 1/3, which is of course the same thing as 1/3 times 6. Because multiplication, when we're dealing with just regular real numbers, is commutative. We can switch it around. With matrices, we can't do that. So that provides one problem. And then another problem is that some matrices are special, that what happens is they kind of destroy information when you try to run things through them. I'll explain what that is in just a moment. But what you end up having to do is, instead of dividing by a matrix, the next best thing is you can multiply by what's called the inverse of a matrix. And so the way you find the inverse of a 2 by 2, now for like a really large matrix, it's a beast to do, and there's ways to do it, but that would take an entire another like lecture. So the way you do it for a 2 by 2 is, let's say your matrix is 4, -2, -7, 2. In order to get the inverse of this matrix, the first thing I need to do is I need to find the determinant of the matrix. Determinant of A. And what the determinant is, there's a lot of different ways to talk about it, but it kind of comes down to, it's like a scale factor that the matrix applies. It's kind of the size of the matrix in a weird way. So the way you do that is you multiply these two entries, and then subtract those results. So we would do 4 times 2 minus -2 times -7. And then what we would get is 8 minus 14. And yes, I did that right. Okay, so we would end up getting -6. So -6 is the determinant. So the first thing I'm going to have to do, and yes, I just erased, but we can rewind. So we have to divide by that determinant. And then what we have to do is we have to swap these two elements. So that becomes a 2, that becomes a 4. And then we have to negate these two elements. We have to switch their signs. So that becomes a +2 and a +7. And that's how you usually find the inverse of a matrix. Or at least for a 2 by 2. Find the determinant, divide by it, swap those two, and change the signs on those two. And so why does that even matter? Why would we ever do something like that? Well, what ends up happening is, remember, when you're doing regular multiplication, if you do 2 times 1/2, that gives you 1. The 2 and the 1/2 kind of cancel each other out until you get what's called the multiplicative identity. Since when you multiply something by 1, the 1 doesn't even matter. So the same kind of reasoning goes here. If you multiply on the left side, because it matters this time, if we multiply A inverse by the left and A inverse on the right, then what ends up happening is A inverse times A, those basically cancel each other out. And what we end up getting is just x equals A inverse times B. Meaning, to find x, I would just multiply this answer by B. And so the way we would do that is, let's actually set it up. I'm not going to use quite so many colors this time, so let's see, that simplifies to -1/3, -1/3, and I apologize in advance if I've made any stupid mistakes here. I don't think I have, yeah, it should be okay. I apologize in advance, and please feel free to correct me. It does happen occasionally. -7/6, and finally -2/3. And then we would set up B, -6, and -12. And so we would do, alright, -1/3 times -1/6, that is going to be 2. -1/3 times -12, that's going to be 4, so 2 plus 4 is 6. I think that's what I was supposed to get here. And then next, -7/6 times -6 is +7. -2/3 times -12 is +8, so 7 plus 8 is 15. So there we go. Now what this is, this answer we've just gotten is supposed to be the matrix X, right? So that's X, and that's Y, since that's what we said X should be in the first place. Or matrix X at least. So what this has done is, what this is doing is, you've taken these two equations, turned them into one single equation, and then solved it using just some matrix multiplication. You don't have to look at it and figure out how to substitute something or see what you have to multiply both sides by like you do in elimination rather. It all just kind of works its way out for you. And the best part is, you can tell a computer how to do this really easily. And so that's another reason that this method is so useful. A computer can do this like that. So the last quick thing, and the real reason you can't divide matrices. First of all, the commutativity thing, the fact that you can't swap them, is part of it, but it's not the real answer. The problem is that certain matrices won't have an inverse. Take a look at this one. Let's say I did 2, 6, negative 1, or negative 6, negative 1, 3. Right? So, the way I would find the inverse of this is I would have to do 1 divided by the determinant. So the determinant is going to be 2 times 3, which is 6, minus negative 6 times negative 1, which is 6. And there we've got a problem. We're dividing by 0. Huge no-no in math. All sorts of bad things happen. Black holes, whatever you want. So basically, this matrix, because trying to find its inverse would make you divide by 0, which you're never allowed to do because it breaks things, this matrix doesn't have an inverse at all, so we can't divide by this matrix. And as you get up in like higher math, you only say that division exists if you can divide by anything other than 0. In this case, this isn't the 0 matrix. We don't have zeros everywhere, but this one still doesn't have an inverse. And the idea is everything that isn't the 0 matrix would have to have an inverse for us to be able to talk about division in the first place. So anyway, that should answer, I believe, the last question about why you can't divide by matrices. Of course, if you got further questions, please feel free to add comments to the video. Other than that, I really want to thank you guys for watching the video, for leaving your comments, and also a huge thank you to everybody at TED Ed. You guys have been absolutely awesome in making all this stuff move, because when I do this stuff, I see it moving in my head, and you guys manage to perfectly make it actually move on the screen. So with that, I think that should close everything. Let me know if you've got any questions. Thanks, guys.